Christoph, you did your PhD at MPA in 2005, and then you move to CITA, and you spend roughly 5 years there. And then you move to Heidelberg, another roughly 5 years, and then you're now head of the cosmological and high energy astrophysics group in Potsdam. You moved in 2017, so you like to move a lot. And you work on a numerical galaxy formation broadly with about large-scale structure, galaxy cluster, with an important twist on cosmic rays and their feedback on galactic scales. So the floor is yours.
Thanks very much. I'm pleased to be here in this sort of ancient theater, and it's great to have you all here. So today I would like to talk about how tiny elementary particles accelerated to large energies can change the appearance and the formation of galaxies. So that's not only my work, it's the work of many. In particular today, I focus on Timon Thomas and Maria Verhan, PhD students that graduated in 2022 and now moved on to their first postdoc. In the background, you see M82, a local starburst galaxy, nearly seen edge on. You can see the edge on disk. And there's a galactic wind emerging from this. And you can see the H alpha in red, the X-ray in blue. So it's multi-phase, this wind. And one of the big questions is, what is the importance of those winds? And what, oops, like this, good. And what basically drives those winds? No, I would like you to sort of first bring up to speed, talk about puzzles in galaxy formation, the galaxy formation paradigm and cosmic rays. And the first big topic, I will then talk about how to model cosmic rays and galaxies, and then to move on of their effect on galaxies. Let's start very simple. I know there are some people who study exoplanets. What is cosmological structure formation? We start with the tiny fluctuations in the density, in the temperature that we can observe in the cosmic microwave background. And this is a blank picture. And we basically know that 100,000 years after the Big Bang, we have tiny density fluctuations at a level of 10 to the minus 5. You can think of those as interferences of primordial waves. Now, if there's a density increase, gravity is stronger, and this causes basically the pull of the surrounding medium and eventually the formation of galaxies and galaxy clusters at the sides of these constructive interferences of these primordial waves, like dropping pebbles into a pond that generates these wave patterns. Now, unlike a pond, where there's a restoring force causing sort of the surface to remain there, gravity is an instability. So you can't basically get rid of this. So the stuff collapses, becomes denser and denser, and eventually forms this large-scale cosmological web that you can see here on the scales of hundreds of megaparsecs. Galaxies now form as beads on a string of these cosmic filaments. So you can't quite see this, but they're little dots. These are dark matter halos, overdensities of the dark matter. And each of these halos hosts a galaxy, as you can see here. At the very center, there's a galaxy forming in this dark matter halo, which is not smooth. This is also coming along with lots of substructures and substructures and so on. And galaxy clusters are the biggest collapsed objects in the universe. They form at the sites where there is knots of this cosmic web, here, here, and here. And all this forms not monolithically, but hierarchically. First, the small things collapse, then the small dwarf galaxies merge to form bigger and bigger and bigger entities to eventually form clusters today. All right. Now, galaxies come in all forms of shapes. Spiral galaxies, elliptical galaxies. Why? And most importantly is the stellar mass that you see here. Let's basically talk about these dark matter halos. They come in all sizes, small dark matter halos, large dark matter halos. And what is shown here is a so-called mass function, as a function of mass. So you find these dark matter halos, and you plot a histogram of those. There are few galaxy cluster-like dark halos, and more smaller dark matter halos. And then you place galaxies inside these dark matter halos, and that function, a stellar mass function, is shown in red, which looks completely different in comparison to the underlying dark matter mass function. Why is this? Well, apparently you need to suppress galaxy formation on a scale that is larger 10 to the 12 solar masses. Some non-gravitational process introduces a scale in galaxy formation. And there's also discrepancy towards smaller galaxies. So either some process lowers the star conversion rate in smaller halos, or our favorite cold dark matter model is not fully adequate and you need to modify it, warm dark matter, self-interacting dark matter, that this slope here is shallower. Let me sort of restate this problem by showing the stellar to halo mass. So you now take the red curve and divide this by the black curve as a function of halo mass. And this is the star conversion efficiency. So filling in gas into our dark matter halos, you ask what fraction of this gas is able to convert into stars. And at the scale of the Milky Way, 20% of all baryons are converted into stars. And this fraction is dropping steeply towards dwarf galaxies, where less than 1% of the available gas is converted into stars. And the same happens towards these giant elliptic galaxies and clusters, where also less than a few percent is converted into stars. That's a big puzzle. So we don't understand on a very fundamental level how to convert gas into stars and dark matter halos. Now, the current paradigm is some kind of stellar feedback is responsible for suppressing the star formation, and stellar feedback runs out of steam on the right-hand side, then we evoke basically accreting supermassive black holes to do the job. And people came up with recipes in these large-scale simulations and showed, indeed, you can form galaxies. And now the race is on to identify the physical processes underlying these recipes to really understand how galaxies form and how to suppress the star formation, star conversion efficiency. Now, one of the ideas that has been floating around is that once you drive out gas out of galaxies, it can't form stars. So this galactic wind paradigm. How does this work? Let's look into the interstellar medium, and once a massive star gets to the end of its lifetime, after a few million years, it dies in form of a supernova remnant, drives a shock wave into the surrounding interstellar medium. This accelerates electrons and protons and can amplify magnetic fields. The collective action of those star formation and supernova then apparently drives the gas out of galaxies in form of these galactic superwinds. And this, so the story goes, is critical for understanding the physics of galaxy formation. This may explain the puzzle of the low star conversion efficiency in dwarfs. Now, how can you drive these galactic winds? There are three general ideas on the market. It's the thermal pressure provided by supernova and AGNs. And clearly, this matters because if you inject 10 to the 51 ergs into a small portion, it drives a shock wave, and momentum conservation ensures that there's stuff flying out. Does it fly out to the heights that are needed to stop galaxy star formation for a long time, so out to the Willow radius? That's not that clear. And in fact, the answer is no. It drives a galactic fountain flow and modulates the interstellar medium. So that's an important process, not responsible for driving out its galactic super winds. The second idea, and this was the number one topic 15 years ago when I did my postdoc, is radiation pressure and photoionization. People said, oh, look, in these AGNs, that's what drives these outflows. Let's assume the same happens in galaxies, problem solved. And the answer is, it's working quite well if you're super dense, if you're a very extreme starburst, but very few galaxies are in this extreme starbursting phase. And you need to have something that drives out the winds also from galaxies that are not as starbursting. There's a third possibility that was very exotic 15 years ago when I and a few other colleagues started this business, and people thought, oh, these are exotic things. Let's let them talk on Friday afternoon in the conferences. And that changed now. The last conference on this topic, there was a full day of this on Monday morning or Monday morning and afternoon. So this is now, I think, a very hot topic. And let me sort of run you through the physics of this cosmic ray feedback, how this works and why this works. So the main idea is that we observe an energy equipartition between cosmic rays, thermal gas, and magnetic fields in the local interstellar medium. Now, the thermal gas cools quickly, the cosmic rays don't, so they stay there. So there's an energy reservoir that cools very slowly and can potentially drive outflows. And this may suggest that the self-regulated feedback loop indeed has cosmic rays that drive this wind. What are cosmic rays? These are fast charged particles. Here's the spectrum of the cosmic rays from GeV. So these are non-relativistic charged particles up to 10 to the 21 eV. So that particle has the energy of a fast flowing tennis ball. And a tennis ball, there are 10 to the 21 particles. Here you have a single particle that has the energy of 10 to the 21 particles. Enormous energies, much faster than any earthbound accelerator can actually get you. Now the flux is over 33 decades here. Here we have 1 particle per square meter per second. Down here we have 1 particle per square meter per year. That's why you need huge observatories like Pierre Auger to detect these ultra high energy cosmic rays. But if you ask where's the energy sitting, if you integrate over this is dominated by these GeV particles because the spectrum is so steep. It's almost a perfect power law. It steepens a little bit and at 10 to the 15 electron volts. That's what we think where the galactic accelerators run out of steam. And it flattens around here, 10 to the 18 electron volts, where we believe that these are the extragalactic population of cosmic rays. But that's interesting cosmic ray science in terms of the feedback. What we have to care is the yellow part of the spectrum, the GeV particles. That's where all the energy sits. And it is that part that is an equipartition with the thermal gas, with the turbulence, with the magnetic field. Now, we have just finished and published in December last year a review on this. So the young postdocs and students that would like to learn more, I can point you to this review. I will now talk about part of this, but you have a 240-page review on all that stuff out there. And if there's something unclear, write me a question. All right, let's start very simple. We would like to understand how cosmic rays propagate in galaxies. A galaxy has a typical size of 10 to the 4 parsecs. The gyro orbit of a cosmic ray, of a GeV cosmic ray in a magnetic field of a microgauss is a quarter of an AU, 10 to the minus 6 parsecs. So there's a linear scale difference of 10 to the 10. We live in 3D space, so that's a 10 to the 30 problem. That's impossible to treat on a particle-by-particle basis. Therefore, we have to develop a fluid theory for a collisionless, non-Maxwellian component. Let's start very simple. Homogeneous magnetic field, a charged cosmic ray proton gyrating around this magnetic field. What happens if this encounters an alpha wave, which is a magnetic perturbation? Well, all of you have learned this at your physics lectures. Let's work out the Lorentz forces. The V going into the blackboard cross B gives a Lorentz force that works basically back there. And before we sort of go there, if we move ourselves into the frame of the alpha waves, the electric field vanishes because then the field becomes stationary. That's very important. All right, so the first quarter of the orbit, there's a V cross B, a decelerating Lorentz force going backward. The next half orbit, the cosmic rays comes out of the board, the magnetic field goes up, and again there's a decelerating Lorentz force. And the same happens for the last quarter of the orbit. So if you have such a configuration, there's a decelerating Lorentz force across the entire orbit of our cosmic ray. Now, whether you accelerate or decelerate depends on the relative phase of your cosmic ray gyro orbit and the alpha wave. So in this sketch, we had a decelerating Lorentz force along the orbit. If you shift the phases by 180 degrees, you have an accelerating Lorentz force and your parallel momentum increases. Now, only electric fields can provide work on charged particles and change their energy. In the Alfvén frame, there are no electric fields. Therefore, the cosmic ray energy is conserved. If we change the parallel momentum, say we decrease it, we must increase the perpendicular momentum to conserve the entire momentum. So that means the angle of the cosmic ray momentum and magnetic field therefore changes as a result of the Lorentz force acting on that cosmic ray. And we call this pitch angle with a pitch angle cosine mu. Now, as we have a resonant interaction like shown in the sketch here, you can see that our cosmic ray of a gyro radius shown here interacts with an Alfvén wave that has a wavelength that is equal to the gyro radius. And you can immediately see by changing the wavelength, you basically move off the resonance. So that's the picture with the Lorentz forces in configuration space. And the equivalent picture is if you go to Fourier space, and there you can simply write down your resonance condition that the Doppler shifted MHD frequency on the left-hand side is a multiple n times the cosmic ray gyro frequency. That's the equivalent statement in Fourier space. Okay? Now, a cosmic ray interacts not with a single Alfvén wave, but with a train of Alfvén waves, and therefore can change its pitch angle. That means the angle between the momentum vector and the mean magnetic field. And that's how our cosmic rays are scattered. They're not scattering by scattering of particles, but by scattering of electromagnetic fields, like the ones I described to you in the previous slide. Now, let's look into the velocity space, parallel velocity, perpendicular velocity. And this is a ring centered on the Alfvén speed, where the energy of our cosmic rays is the same, right? On a ring, as you all know, the energy is the same of these particles. So if you start with a population that moves initially rightwards, the red population, or initially leftwards, you have scatterings and you change this pitch angle. It means you move on this circle. Okay? In fact, you have a random walk. You increase, you decrease, depending on the local phases relative to the Alfvén waves. And a random walk, starting from this distribution like this, smoothes you out to eventually become completely flat on this velocity circle. Okay? And that's a diffusion process. So you can describe cosmic ray propagation in velocity space as a diffusion process in this pitch angle, and you basically then isotropize a population in the frame of the moving Alfvén waves until this whole thing becomes then flat. All right. Now, there's more physics to this. If you now have cosmic rays that move along a magnetic field, they scatter on these Alfvén waves. And if they're faster than the Alfvén waves, they drive the Alfvén waves unstable. The Alfvén waves grow. And they grow at the expense of the mean momentum of the cosmic rays. They're slowed down. So you have a transfer of energy from the cosmic rays to the Alfvén waves via this scattering. And that's how this instability works. This slows you down to the Alfvén speed. And then in addition, you now grew Alfvén waves that get damped via different collisionless damping processes. That means you start with cosmic ray energy. This grows waves. These waves get damped, and this produces heat. And this is how you couple cosmic rays to the surrounding plasma. And this is how cosmic rays can exert a pressure on a thermal gas via scattering on Alfvén waves, not by colliding with the particles. This happens way too rarely. If you have a weak wave damping, that means the wave field remains strong. It can scatter the cosmic rays. You have a strong coupling, and this causes the cosmic rays to isotropize in the wave frame and to stream with the waves. If the wave damping is strong, the wave level is low, scattering is inefficient, there are less waves to scatter, you have cosmic ray diffusion. All right. So there are three modes of cosmic ray propagation. First of all, they gyrate around magnetic fields, and the magnetic field is flux frozen in the plasma, so they're advected with the magnetic fields. And along the magnetic field, they can either diffuse, and you all know how the diffusion solution looks like, it's a Gaussian, or they can stream. That means they isotropize in the wave frame, and they're basically moving with the alpha waves. And you can see that the outcome looks quite different. Real life, all the three processes happen, and we would like to know what fraction of the processes happens at what time. Now, some of you probably know radiation hydrodynamics. This theory has been developed in the 80s and the 90s. And there's a great analogy of cosmic ray and radiation hydrodynamics. If you have tangled magnetic fields, you have strong scattering, and that means you have a diffusive transport. And that corresponds to diffusive transport in a clumpy medium for radiation hydrodynamics. If you have a resolved magnetic field and strong scattering, you stream with the alpha speed, and that corresponds to Thomson scattering and advection of radiation with the flow. If you have weak scattering, you have streaming and diffusion. This is flux-limited diffusion with an optical depth of order unity. If there's no scattering, cosmic rays move at the speed of light, very close to the speed of light, and so does light. So it looks like the two are very similar in terms of propagation. But cosmic ray hydrodynamics is charged radiation hydrodynamics. We have to account for the Lorentz force and for the anisotropic transports of cosmic rays along the magnetic field. That differs from the radiation case, which can just propagate isotropically. Now, taking these ideas, the analogies of cosmic radiation hydrodynamics, we derived a two-moment system for cosmic ray propagation, starting with the cosmic ray Vlasov equations. And that's the resulting lab frame equations for the cosmic ray energy and the cosmic ray flux. So before I discuss all these details, let me just flesh out the radiation hydrodynamics equations. And you can see the two look very much alike. Okay? So here's a pressure tensor that basically drives the propagation, and there are source terms on the right-hand side. There are two differences. There's a W, which is, it's the speed of the gas plus or minus the speed of the alpha waves. You isotropize not in the frame of the gas, but in the frame of the moving waves, forward and backward moving waves. And you have to project the fluxes onto the local direction of the magnetic field, unlike in the case of hydrodynamics. But the rest is very similar, except for the Lorentz forces that you have to take into account. Okay, now the problem is exactly these Lorentz forces. You have to solve the cosmic lab frame equations for the rapid gyrokinetics. You didn't gain anything because that is forbidden, that is impossible to do on a galactic scale. The clue is you transform to the co-moving system, then you can project this out, and you're left with a little bit more complicated equations because you now introduce pseudo forces from this frame transformation. Like if you go on a merry-go-round, you have the centrifugal force. The same happens there. A few of these terms are centrifugal forces, so to say, for cosmic ray hydrodynamics. But let me sort of give you the picture here instead of looking at the formula. So the question is now, if the cosmic rays are fast, they will lose energy to grow alpha waves, which are initially slow, and gain the energy. Okay, that means you slow down cosmic rays by growing alpha waves. Or you're on the other side, that the alpha waves are fast, the cosmic rays are slow, so the alpha waves will lose energy by accelerating cosmic rays. And that's what these equations basically compute. They tell you in which regime you are and how fast do the cosmic rays push. Now, let's show a very simple example. That's the cosmic ray energy density, the cosmic ray flux, the forward and the leftward moving alpha waves. Let me start this movie. And you can see the cosmic rays are moving outwards. Fine. Let's focus on the alpha waves. Suddenly, everything else is damped except for this part, which is driven unstable by the flux of outwards moving alpha waves. And the same happens on the left-hand side. And the level of this flux determines how often the cosmic rays get scattered and how diffusive the solution is, basically. So here, the only thing I changed is the level of damping. Red means I damped the alpha wave field strongly. This means the flux is larger and the solution is more diffusive. If there's less damping, there are more alpha waves that modulate the flux, and it's more streaming-like, it's more boxy. So this allows me now to compute the diffusion coefficient locally as a function of space and time and tell me how closely you couple the cosmic rays to the thermal gas. How much pressure is actually given to the gas, depending on the level of alpha waves that you have there. The beauty of the thing is it computes streaming and diffusion along magnetic field lines in a self-confinement picture. So the cosmic rays drive their own waves that scatter them. You don't need any pre-existing wave field. The moment expansion is similar to radiation hydrodynamics, a well-tested theory. It accounts for a lot of kinetic physics, nonlinear Lano damping, chair-resonant instability stuff that was not included previously in the old methods for cosmic transport. It's Galilean invariant on the causal transport and energy and momentum conserving. Let's look at this ring magnetic field. And this is initially my distribution of cosmic rays. And as you can see, as the thing moves on, cosmic rays are scattered. They drive this unstable. They don't diffuse perpendicular to the magnetic ring configuration. Well, we see a little bit here, which is numerical diffusion. That is basically also wanted because there is some physical cross-field diffusion, but mostly it's diffusing along the magnetic field at the alpha speed. All right, so theory is nice, but we would like to test it. And when we were just done with the theory, this map came out, which you all have seen. It's the MeerKAT image of the galactic center, one of the most beautiful images I've ever seen in the last years in astronomy. It's almost too bright here to see this, but really go MeerKAT galactic center and zoom on. It's amazing the level of detail that you see there. In particular, there is strange looking filaments all over the place. And in particular, those filaments were quite interesting to us. What could this be? First of all, I mean, what you could see is there are these stripes of synchrotron illuminated filaments. Clearly, these are magnetic fields, but why is it like this? Why are these stripes sorted according to the length? So one idea is that we have some uniform magnetic field, and there is a there's a massive star that drives a stellar wind out there. This stellar wind shocks. There's a contact discontinuity, and there's a bow shock as a result of the movement of the star relative to the ISM. As the magnetic fields come in, they're bent here, and they come into contact with the contact discontinuity. That means cosmic rays that accelerated at a termination shock can hop onto the field lines and leave this region here. And the question is, how fast are these cosmic rays transported? Are they diffusing along the magnetic field? So that's what you read in every textbook. Or are they streaming and diffusing? So do these synchrotron filaments look like this here? Now, Thomas, who introduced and built this theory for cosmic ray hydrodynamics, took this, what we call radio harp, because it looks like a harp, with the strings being magnetic flux bundles, and plotted the surface brightness for the first, the second, the third, and the fourth bundle. And the first thing he tried is diffusion, because textbooks tell you cosmic rays diffuse. And that's a horrible fit. Nature does not want cosmic rays to purely diffuse. Let's test our new model for cosmic ray hydrodynamics, where streaming and diffusion takes place, using the parameters of the galactic center. Hey, That looks much better. Indeed, I think that's the first evidence that what I have told you actually happens in nature. So you populate these magnetic flux tubes, and the cosmic rays move along these magnetic flux tubes. They excite alpha waves, those scatter those, and basically then you can only move them out at the speed of the alpha waves along these magnetic flux bundles. And especially at late times where the theory applies, this perfectly describes what you see in a synchrotron emission. All right, moving on. I convinced you that what we do is at least partially, or depending on how convincing you found this experiment, fulfill in nature. What does it do to galaxies? Let's start with a simple experiment, a rotating sphere of dark matter filled with gas. We switch on cooling. The gas is densest at the center. It cools fastest, conserves the specific angular momentum, starts to form a disk. And what are the conditions for driving now these winds out there? Now, what you can see here is vertical profiles from the disk. And you see the cosmic ray velocity in blue, the alpha in speed, and this is the gas. At some height, suddenly the gas gets accelerated and moves outwards. How is this working? Well, you can see that the cosmic rays, the blue curve, minus the orange curve, this is this one here, is basically coming close. So the cosmic rays are coupled in, and then they're pushing on the gas and driving the gas out there. That's exactly what is happening, and this accelerates the galactic wind. So the alpha waves are supported by the thermal plasma, and therefore the plasma itself gets accelerated. Now, let's look at the force densities. So what pushes, in fact? Cosmic rays blue dominate, in fact, the force density as a function of height. Green is the thermal gradient, thermal pressure gradient, that is secondary to the cosmic ray gradient. The magnetic field alternates between two portions. That is strange. And let's look a little bit closer what happens here. This is the magnetic pressure, the dark, and the light is the magnetic tension force. Because magnetic field lines not only have a pressure that pushes on the magnetic field lines, but if you have a curvature, this also wants to string back. So you can think of magnetic fields as elastic rubber tubes there. Now, why is this apparently much less compared to the pressure gradient? And the answer is by looking at the three-dimensional configuration of the magnetic field in our simulation that grows self-consistently. Now, because of this outflow, the magnetic fields are stretched in the inner part. And you can see here that the magnetic field is mostly vertical. The further you go out, you see a helical field structure emerging. So coming back, this is the magnetic pressure minus grad B squared. The magnetic tension is B dot grad acting on B. If you then simplify this for a vertical magnetic field, ignoring the toroidal field components, you have basically minus dz bz bz and a plus bz dz bz. And that means it cancels by a factor of 30. Okay, so that's why magnetic pressure is irrelevant because of the magnetic tension force that exactly cancels this for vertical field components. That's why magnetic fields are not very good in launching this wind, why you need, in this case, cosmic rays to really move the gas off the disk. These are the wind properties. So it's a low density wind that is hot. That's the cosmic ray energy density. Now, there are very few cosmic rays here because they used up the energy to drive the wind to actually heat the gas. That's why the wind is hot in there. So that's the velocity of the gas. You can see the stuff is flying off the disk. And of course, down here is flying to the bottom. Now, I told you that we can also calculate the cosmic ray energy density, which is important for the diffusion coefficient that is shown here. And this looks strange. This looks like there are holes in the energy density. What's going on here? Why are there some regions that have no energy density in the waves? That means the diffusion coefficient is almost infinite. The cosmic rays are almost sort of not coupled. Let's look what a magnetic field line does by going through this here. And that shows that the cosmic ray velocity along this magnetic field line, as soon as it populates this region without alpha waves, goes down. Why? Because the gradient projected on a magnetic field is very long, because it's almost perpendicular to cosmic ray gradient and magnetic field line. A long gradient means you push slowly. Cosmic rays are slower than the alpha waves. That means the alpha waves accelerate the cosmic rays and lose their energy. The green one, the cosmic rays are faster than the alpha waves. That means the alpha waves gain energy if you don't pierce these regions. That's the region where the cosmic rays are slower. Okay? So this means the cosmic ray diffusion coefficient is a strong function of energy density, magnetic field density. It's not constant. That's the bottom line. So the old versions for cosmic ray transport assumed a diffusion coefficient of 10 to the 28 centimeters squared per second. This is the simulation that goes one step beyond and tells you, no, that's the wrong assumption. There's much more richness in the physics. And if you do it right, you basically see this. All right. So I talked about the magnetic field as if it were there forever, but the magnetic field is something that has also to grow. How does the magnetic field grow? Well, first of all, you need to make the magnetic field. And there are two ideas around. Either you go to some electric current source by a phase transition in the early universe. And that's quite dicey business still today. So we don't know whether this actually exists. The other thing that is definitely happening is the so-called Biermann battery. Okay, so that means that we have a baroclinic flow, and that can provide you sources for the magnetic field that are tiny, 10 to the minus 20 Gauss. So it makes magnetic field that are irrelevant. But once you have them, you can grow the magnetic field via a dynamo. How does a dynamo work? Well, you have your magnetic flux tubes, basically, and circles. You stretch it, you twist it, you fold it, you cut it, and then you gain 2 circles for 1. Then you do this for every of these circles. You get 4 circles, 8 circles, and you can see that this exponentially amplifies the magnetic field. That's what a magnetic dynamo is. It turns kinetic energy that is used to stretch, twist, fold into magnetic energy. And this goes up to the point when the magnetic field is strong enough to resist these stretching and bending motions. And that's when you saturate the dynamo. So this field growth then stops at a sizable fraction of the turbulent energy density when the magnetic forces become strong enough to resist this. Yes? So, great question. Well, you need basically a subsonic turbulence. You need eddies, basically. Okay? And as long as you have eddies, you have the stretching for free. And there's always then in the third dimension, because of the way you generate this, the vorticity is generated, there's always then some bending motion, and that automatically happens there. Now, proving that this picture, in fact, works, to my mind, has not been done. That's the sort of story that Zeldovich taught us in the 70s, I guess. Now, really sort of looking that exactly this happens, I think this is the picture behind this, and I show you now evidence that something, at least on the left-hand side like this, works, but really identifying individual things is difficult in something like a turbulent flow pattern. That's something for the young generation maybe to come up with a brilliant statistics to really identify this. That's a great question. Okay, now using the same model I talked about, simple collapsing halo filled with gas, it collapses, starts to form a disk. Does this have a magnetic dynamo? First of all, I run several of these halos, a Milky Way, a large Magellanic Cloud, and a dwarf galaxy, in 2 different models where purely advect cosmic rays and they also have diffusion. And that's a star formation rate. You first get a starburst that then exponentially decays with time. And you can see that cosmic ray feedback suppresses the star formation in smaller galaxies and not so much in the bigger galaxies. On the right-hand side, you see the energy budget. That's the thermal energy in solid for the three differently colored galaxies. The cosmic ray energy dash dotted quickly comes into equilibrium in all these three cases. And magnetic field also grows and comes into equilibrium in the case of the Milky Way and stays below the thermal pressure and the cosmic ray pressure in the dwarf galaxy. Let's look at this magnetic growth a little bit more in detail. First of all, where does it saturate? Now I compare the turbulent energy dash dotted with the dotted energy, and you can see that indeed the magnetic energy saturates at the level of the turbulent energy density, as expected for a small-scale dynamo. Now, this is only good to factor of a few, so that is something to bear in mind there. Rotation, by the way, dominates. We have 100 times more energy in the rotation, but you need this sort of stretching and folding, and a rotation simply stretches the field. It doesn't do any folding. So that's why you can't use the pure rotation energy to grow the magnetic field. This shows now how the magnetic field grows over time. It shows the magnetic field strength as a function of density. That's my initial field that I put down by hand. And you can see that initially, as the gas collapses, it adiabatically compresses the magnetic field. So the field strength grows with a density to the 2/3. That's what you expect for an isotropic collapse. Next, what you see is that there is an increase of the magnetic field strength at the smallest scales, the highest densities. So these are the eddies that have the shortest dynamical times. And this then migrates to lower densities. That means to larger scales as time goes on. That's interesting. Let's look a little bit more. So now I do a resolution study. I run my galaxies with 100,000 grid cells, 1 million, 10 million grid cells. And you can see the magnetic field grows faster for the higher resolution. And then once you afford 1 million gas cells, you numerically converge here. Okay, so that's something, bear in mind this, numerical convergence is important, and this depends on the type of code that you actually run. So if you have a moving mesh code, this has a smaller numerical convergence than a fixed mesh code, because the flows are relative to this gas cell. This introduces numerical errors, and that's something you have to basically make sure that this is as small as possible. Now, let's zoom on to this Milky Way galaxy at the very beginning. First, the growth is independent of resolution. That's what you expect from an adiabatic collapse. Okay, so the magnetic field first grows adiabatically to this point, at which point the growth rate depends on the resolution. And that's what you expect for a small-scale dynamo, where the growth rate scales with the square root of the numerical Reynolds number. Now, we only can afford a Reynolds number of a few hundred. Now, in real life, this is, of course, much larger, but it doesn't matter, because in real life, this would be very strong shooting up there. This demonstrates that indeed what you expect is that the magnetic field grows like what you expect for a small-scale dynamo. So how do you inject the turbulence that you need for this? First of all, you have an accretion shock that moves outwards. This accretion shock is corrugated. You can see these sort of corrugations here that dissipates kinetic energy of the sort of collapse into vortical motions, and this then drives the dynamo to grow the magnetic field that you can see here. Now, once the accretion shock has moved out, the turbulence it excited is slowed down, and we enter a second phase where there is a cold galactic disk that rotates quite fast in a slower rotating circumgalactic medium surrounding and embedding the disk. That means you have a Kelvin-Helmholtz instability at the interface, and because it's cold, it's a supersonic dynamics instability. That means you get the entire disk unstable. This is what we call a body mode. You excite these body modes. This drives also turbulence and sustains this magnetic dynamo in this disk. You get a further growth of the magnetic field. And these are the final plots I would like to show you. This shows the power spectrum, the kinetic power spectrum, solid, the magnetic power spectrum. And you can see that time goes from 0.1 gigayear in yellow to 1 gigayear in dark. And you first grow the magnetic field on small scales until you come into saturation with that. And then you grow in size. You basically go to smaller and smaller K values, like what you basically expect for these dynamos. And there's one thing for the experts in the audience that did not match. This was the slope on large scales. So this was proportional to K squared and not to K to the 3/2, which is the Kazantsev theory. And the reason for this is easy, because this applies to a homogeneous box. Now we have a galaxy that is an exponentially stratified density and magnetic field that it has from the adiabatic collapse. That means you need to take into account the form factor of your exponential. That's a Lorentzian. That's exactly this K squared. And on top of this, there's then the Kolmogorov slope that you basically see. And if you then cut out the central part that has a strong radial dependence of the density, you can see the Kazantsev slope from 1 to 5 kiloparsecs. So that's exactly what you expect, like a textbook story. So that is, I would say, quite strong evidence that you grow the magnetic field via a small scale fluctuating dynamo to saturation. And how you order the magnetic field is not that clear. It could then be a second phase where you actually drive a large scale dynamo. There could be some MRI modes excited. There could be stretching of magnetic field lines. This is less clear. But I think that is now quite clear that the growth of the magnetic field to saturation is done via a dynamo. And let me close the talk by telling you, well, we can observe this. And that's work done by Maria Verhan, where I used in the same simulations. And I have advection, anisotropic diffusion. And then we compute steady state spectra of protons, primary and secondary electrons. Now, previous theoretical modeling assumed either one zone models. You treated the galaxy as a single zone. You guessed your parameters and you calculated radio and gamma ray spectra. Or you had 1D transport models or static Milky Way models like GalProp or other models. And here are the two observational evidences that indeed there's a scaling relation of the radio and the far infrared emission. They correlate. This is known for 50 years. This was basically remaining unexplained for 50 years. And just in the last 10 years, there's this gamma ray infrared correlation that was basically come into being because of Fermi. And clearly, there is an overall paradigm that star formation that is responsible for the far infrared emission. So it emits UV photons that are absorbed by the dust, re-emitted in the infrared. Then the dying stars make supernova, accelerate electrons. Those shine in the radio, and this is clearly correlated through the physics. But is this actually the full story? And to understand this, we run MHD cosmic ray simulations of galaxies of different halo masses and star formation rates, model steady-state cosmic rays, protons, primary and secondary electrons, model all radiative processes. And today I focus on the radio part to understand the dynamo and the electrons. So that means we solve this equation, which is a simple equation for a spectrum of the electrons in every cell of our simulation. So for the protons, we account for all possible loss processes, Coulomb, hadronic, and escape losses. In the electrons, we additionally account for inverse Compton synchrotron losses. Primaries are electrons accelerated at the supernova remnants. The secondaries are the electrons coming from proton gas collisions of the ISM that make pions and decay into muons and secondary electrons. Now, the first question you may have is steady state good enough? And the answer is, it's basically good and bad at the same time. So for half the cell, the time scale to reach steady state is fast enough compared to the time scale on which the cosmic ray energy density changes. So those are the cells rightwards of this. The other half, if you're in an outflow close to supernova remnant, the cosmic ray energy density changes faster than the time you reach steady state. The good message is that if you then weight these cells by the synchrotron emission or the gamma ray emission, most of the cells are in this regime where steady state is a justifiable assumption. Good. Okay, now we move from a starburst, that's the density, the protons, the electrons, to a Milky Way. And you can see the disk growth, the emission drops. First, we would like to check whether the observed spectra of cosmic ray protons, blue, and cosmic ray electrons match what we observe with the AMS and the Voyager spacecraft. Voyager has now passed the sort of boundary to the interstellar medium. It is now taking data in situ of the local interstellar medium, and in fact, came back, the data that it actually sent to us told us there are more cosmic ray electrons compared to cosmic ray protons at low energies. So that's one of the, I would say, biggest findings of Voyager. After 30 years, it flies there. It basically posed a puzzle. And it's quite easy to understand now in these models because Coulomb cooling is effective as soon as a particle becomes non-relativistic. That's why the proton spectra turn down, but the electrons don't turn down for another factor of 1,836, the mass ratio. And it's nicely otherwise on the data. That means we can also explain the positron fraction as a function of electron, as a function of energy, except for this part which rises, which is possibly due to pulsars or supernova remnants close by, which we do not model here. I don't think this is a sign of dark matter interactions, unless all the hundreds of papers that have been written on this topic. Now, coming back to our simulation, that's the density, the cosmic ray energy density, the cosmic ray to thermal pressure ratio, which dominates in the outer part of the cosmic rays, and it's less prominent at the inner part. There's an equipartition right around the solar ring at 8 kiloparsecs from the center. Maybe it's a right, maybe it's a coincidence. That's what the simulations give you. That's now the electrons. These are the magnetic fields that grew via this dynamo, and that's the synchrotron emission for the Milky Way, for dwarf galaxy. What we do now, we populate this far infrared radio correlation with our simulated data points, and the open data points show the observations. And if you sort of look what happens for a single galaxy, it first moves up and then it moves down the relation. This moving up is simply the dynamo. Galaxies that we observe in the local universe have long passed this moving up point. This happens at the protogalactic stages at redshifts of 6. So once you saturate, you are on a relation. And you can now start to study the individual sort of deviations, the scatter in this relation. In fact, if you look face on, you see the entire magnetic field, which is perpendicular to your line of sight. If you look edge onto a galaxy, half of the magnetic field points at or from you. That means it doesn't show up in your synchrotron emission. So that means it drops these fluxes by a factor of 2, et cetera, et cetera. So lots of interesting things now to study there. Most importantly, this basically assumed a universal conversion from star formation to cosmic rays to radio. And people said, well, then you should have steep spectra of the radio. That's not what we observe. We observe flatter spectra. These are the data points. This is the synchrotron emission of our models. That is why this colorimetric theory has been discarded for the last 20 years. Well, we have simulations, we can simply add in the full physics. We can add in free emission, and we can add in thermal synchrotron absorption. And if you do this, then the resulting emission is right on the data points. Okay, so the answer is this simple colorimetric model is correct because you need to account for free emission and for synchrotron absorption at low frequencies. And in particular, in the centers where there's more absorption, the spectra are even flatter. That's what the models automatically reproduce without any tweaking. Let me come to my conclusions. So I showed to you that a moment expansion similar to radiation hydrodynamics allows us to construct a novel theory of cosmic ray transport mediated by alpha waves that we then couple to MHD. And this allowed us to successfully explain this synchrotron harps that is now seen in the galactic center by MeerKAT. A small-scale dynamo growth magnetic field to equipartition with the turbulent energy density. Cosmic ray feedback drives out galactic winds and slows down star formation. And these models reproduce the global far-infrared radio correlation for saturated magnetic field, and the scatter is due to wing angle and cosmic ray transport. And most importantly, synchrotron absorption and free emission is required to flatten the cooled, steep synchrotron spectra. Thanks very much.
Yeah, any questions?
Hello, I'm high energy cosmic ray physicist, so you don't need to tell me how important is anisotropic diffusion of cosmic rays. In your model, could you explain the large scale structure of magnetic field of Milky Way like galaxy in halo?
So the halo is more complicated because there we believe that cosmological accretion shapes the circumgalactic medium surrounding the disk. Yes, so that is in these galaxy formation models shaped by cosmic accretion and outflows. And the accretion is something we can compute in these cosmological simulations I didn't have time to talk about today. But the outflows in all current cosmological models are not really shaped self-consistently. We are working on sort of now putting in the right physics to form these outflows self-consistently there. So yes, we have simulation models that give you some magnetic field in a circumgalactic medium that may or may not be the true field, because that misses still some of the right physics, I would claim.
Okay, and the second question, what would provide you escape of cosmic rays locally to explain the primary to secondary ratios? This model.
So
this vertical component is very small locally.
So you mean this bit basically? So this is simply the normal thing. This is the energy dependence of the diffusion coefficient. That's why this goes down. And this going up is basically just a local source.
Yeah, that's another story. Okay, maybe I will.
Okay.
I had a question, a clarification regarding your point that you need cosmic rays to drive winds. So I'm a bit puzzled because I have colleagues who have been pretending to drive winds for 30 years. So
excellent question. So the field of galaxy formation has first seen semi-analytic models. These are colleagues like Carlos Frank, Simon White, that have basically claimed to solve galaxy formation using the dark matter merger tree and some simple differential equations they computed, which had basically bathtub model type of style. The next generation of hydrodynamic simulations assumed recipes that drove the winds by decoupling gas temporarily from the hydrodynamics and couple it back in, or by accumulating enough energy until you dump a lot of energy in there. So I would say these are recipes that had emerging winds, but the cause of these winds was put in by hand. And now I would say the recent 5 years, people have started to put in real physics. So there are some colleagues that use then a fully resolved multi-phase interstellar medium with a supernova remnants. And of course, you have fountain flows, no question. Then the fountain flows are more important in low mass galaxies. It looks like they're not sufficient to drive the winds out to large radii. That means you need something else. And that's, I think, slowly now the picture that we have, that you need the supernova feedback to self-regulate the ISM to drive fountain flows. And then you need the cosmic rays to furthermore accelerate this, like a sort of a second boost in a rocket the first booster system are needed to launch it, but to accelerate the rocket, you need a second phase, and that is what I think are the cosmic rays. Radiation can't do this because up there, radiation is not very efficient in coupling momentum into the gas phase. Now, I would say any model that drove the winds large scales is basically intrinsically put in by hand the winds. It's not emerging out of modeling the physics. It's not saying this is worthless. I think this is extremely important and interesting science that these people did. So they, in a sense, did, assuming there is a wind, we form galaxies that look like real galaxies. But now we go back and say, okay, but what actually drives these winds? And are the winds as strong as these models have assumed? And if you're there, then I would say we solve galaxy formation. We are not yet there. So for instance, if dark matter is not cold, but is self-interacting or is a warm component, you can't tell right now because they tuned the wind efficiency such that they fully reproduce the galaxy's stellar mass function. And that means they assume that this drop of star conversion efficiency is fully made up by feedback. Maybe only half or a fraction of this is feedback, and the other half is in fact dark matter physics. So right now we would not be able to tell them apart. And that's, I think, what we want to do. We want to sort of have fully predictable models for galaxy formation, and we can see whether cold dark matter and these physically inspired models are able to solve this problem or not. That would be really cool. Then we learn something. Right now, I would say we are in this intermediate phase. So we don't quite know whether feedback solves it all or part of it.
Other questions?
I was curious about the saturation of the magnetic field. You said that it happens very quickly in the early universe around redshift 6. Is there anything that can disrupt it so that you have to go through another phase of growth and saturation?
So I would say, given our current notion of Reynolds numbers, which are huge, and especially the magnetic Prandtl numbers, I would say no, because we know now from JWST and at ALMA that early galaxy formation is very turbulent. There is turbulent star forming clumps, basically, that are proto-galaxies or the first galaxies. And that's fully turbulent, that's guaranteed. That's basically what we know. And in such a situation, plus Biermann field that you typically get from ionization fronts, from the first stars and so on, where you have basically corrugated shocks, you basically are guaranteed to have our 10 to the minus 20 field by redshift, I would say 15, 20. Taking this tiny field, taking the turbulence we now observe between redshifts of 12 and 6, it's almost inevitable that you get a saturation. Now, this is typically tiny. The growth and scale of the field, that depends on more physics, alpha omega dynamos and stuff we are less well understood. But I would say growing the field to saturation is almost inevitable.
Are there any other questions? Okay, I can ask you a few, I think. So maybe one would be sufficient. So for the launching of cosmic ray-driven winds, what is the most important? Is it if you artificially separate diffusion and streaming, for instance? Is one more important than the other?
I think the launching is supernova, just the mechanical energy from supernova, basically. And then for the acceleration, it's a cosmic ray flux that is basically, so back then we are now talking about scale heights of 1-2 kiloparsecs above the disk. That's where ioneutral damping is not anymore efficient. That's where possibly non-Landau damping affects the level of a waveframe. So that's where you're mostly in the streaming picture. That's what we also see. So I would say you definitely need to get the streaming physics right, because this is then basically important for really pushing up the cosmic rays and to pushing up the gas then to the world radius. Because if you look at the successful models, Eagle, TNG, Illustrious, they all have an emerging wind out of their recipe-based launching that goes to the Will radius. And that is something I think you will not get, or half the Will radius. That's something you will not get without cosmic rays. At least that's the only physical ingredient I know that is able to push the gas out to these large heights.
Okay, thank you. So if there's no other question, I think we can stop here. And thanks, Christoph, again.